should be perhaps, from practical point of view, interesting and important to you. The first remark before starting the lecture is that this is a so-called summer school. It means summer, I don't have to define summer, what does it mean? It's pretty hot, humid. The second part of the phrase is school. That means that I will deliver to you a talk and we will make interaction with you. That means sometimes if you have questions, then don't hesitate to put your questions. Anytime, anywhere also, that I'm sitting. I will provoke you to put questions. Not only ask you, but provoke you. Because this is, according to my opinion, this is the best way to study. And to understand a little bit deeper than if you are studying alone, facing with a book, then you cannot pose questions. But this is a pretty unique situation. You can face with an instructor or with a series of instructors. So please do not waste the possibility to pose questions. So anytime, I stress again, anytime you have questions, you do not understand something, then please do not hesitate to interrupt me. In this case, you will be encouraged to interrupt the lecture. So this is not a formal lecture, although it is projected and recorded and a lot of other things, which is needed to be done. But you please do not forget, you are sitting in a school, in a summer school, and your task is partly to put questions if you do not understand something. So if you lost something, you lost the thread of the idea, don't hesitate to interrupt me and ask. Raise your hand. Okay, maybe you don't have to raise your hands, but please interrupt me and ask the question. This is the first. Second one, that I have to use a foreign language. This is not my native language. And I think that many of you use English as a native language. I learned it when I was, say, much smaller and thinner and now, but this is still not a native language. So if you do not understand something because of my strange stress or dialect, then again, do not hesitate to ask me again. This was not quite understandable, please repeat it. And I will be more than happy, I can't say, but I will be ready to repeat. So please do not hesitate if you have any language problems. That's a secondary problem. You can use, I don't know the native language, this will be a problem with the communication, but if you have just problem with the language, that's actually not a problem, it's a technical problem. I'm also struggling with the language as you are probably do. This was a second remark. Third remark, I don't have any third remarks. I will start the lecture. The third remark, it comes into my mind, that this is in order to stress the feature of this school, as it is a school, I collected a couple of homeworks at the end of the lecture. So your task is not just sitting here and drinking tea or coffee or whatever, or just sitting in the warm tea and then just your ideas kind of walking far away from here. But these type of homeworks will bring you back to the reality, to here, to this summer school, and try to solve these problems. If you have any troubles solving it, then consult the instructor. I hope that this lecture will be put to the internet or to the homepage of the conference of the summer school, so it will be pretty easy to get access to these pretty simple problems. I had also the troubles how to fit my idea take-home messages to the general background of knowledge of the audience, and I decided to select a more or less neutral subject. You can see this is pretty general, and I think that everybody can understand it independently of the background in optics or physics or laser physics. So I try to be so clear as possible. From the students majoring in physics, at that moment, at this place, I will beg your pardon because the details were not so trivial and not so well clarified as it ought to be done. But I have to give some general level, keep the general levels, and I also keep the interest of other students who are mainly majoring in medical or life sciences and not so deeply involved in physics. So I will try to keep the level in the middle. Some parts of the lecture will be not well elaborated, not so deep as is required, and if you observe it, you can show it and it can be better understood, better solved, but because of the time limit, it cannot be done, and I beg your pardon for those students who will observe it or require for a deeper analysis of these problems. Okay, no more remarks because all things will be devoted to the remarks and not to the lecture. So the title is what is the specialty of the laser light? Why is unique the laser light? Because some mystery is always around the laser light, and you can ask whether the laser light is unique compared to other so-called natural light sources. The natural light sources, I will tell it as thermal light sources. Thermal light sources, immediately I will show the next slide, will show you a couple of thermal light sources. On the left-hand side, you will see a couple of pictures of thermal light sources which emit light because of the higher temperature, simply to say. For example, the sun, with a central flash lamp. Flash lamp is English torch, but better to say flash lamp, which can be a continuous wave, or a tungsten filament, the bulb, is very familiar to you, or a welding arc, also very familiar to you. All these light sources emit light because of the higher temperature than the surrounding. These light sources will be called thermal light sources. And on the right-hand side, I listed a couple of lasers from different sorts of lasers, colors, arrangement, etc. Tomorrow in the next morning lecture, you will listen surely a lot of lasers which coming from solid states, dye lasers, laser diodes, etc. These are all various sorts of lasers. This will give you also light as through the thermal sources. What are the differences between the two lights? You will see only the light and not the source. Can you decide whether the light which is coming into your room or eye coming from a thermal light source or a laser? This is a very essential question, don't you think so? I thought this is very essential, especially when some mystics is also giving these problems. The laser channel. Oh, could be a mystic thing, no? And from that point of view, who somebody expects something unexpectedly from this lecture, I have to little bit disappoint them, and it's better if they leave the lecture right now, because the solution to this problem will not be any more so enthusiastic as you suspect to do. So practically at the end of the day, there will be a take-home message. But in the beginning, I will tell you that do not expect too much from the separation of the thermal light source and laser light source based on any of these properties. Actually, you cannot make a clear-cut distinction. There are some parts which can be said that this is unique to the laser light and unique to the thermal light source, but in general sense you cannot make such kind of distinction. Unfortunately. That's the life. What about the directionality? This is the real difference between the thermal light source and lasers. We will see that actually not. Small spot size or time focusing could be, but is also not the required unique feature. We will see why. High energy, power, intensity, and brightness. Also in the morning lecture we heard a lot about it, and I will tell also a couple of additional things to this subject. But it's also not so unique. This is characteristic for laser light, no question about that. But from the thermal sources, we can also get pretty high energy. For example, if we focus the sunshine, it's also pretty high. The brightness can be also high, it can be made pretty high. So this is also not very, very unique. Monochromaticity, spectrality, no, that's something close that we can think about it. Because here you can see a nice green, blue color, etc., etc. The monochromaticity is pretty small generally in lasers. But this is not unique to the lasers, because I can construct lasers which do not have such kind of spectral purity. And I can use a very nice monochromator set in the front of the sunshine, for example. And I can get so small line widths with the laser, with the light, that you can wonder. So it's also not a very, very unique feature. Perhaps coherence. Oh, that's very close. Because the coherence is very much something to do with the generation of the light. And this is the basic difference between the thermal light and the laser light. How to generate the light. And this question, this property, the coherence, is somewhat closer to the answer of this question, but we will see that it's also not a unique and distinct feature of the laser light or thermal light. We will see soon. What remains in the list? The photon distribution. We will see. That would be very close. So we will be very close to solving the problem, and we will see it soon in the lecture. So we will run through these properties, very great steps, and we will try to answer the question, what is unique in laser light? Some additional other slides focusing into this problem. Let's do an experiment, very simple experiment, and I borrowed a picture from Wilhelm Herschel, who discovered the iron part of the sun radiation. These are the thermal elements he measured that, although we don't see the iron part of the spectrum, there is still some energy falling to it, as we discovered it. But I use now the picture to demonstrate the problem. So we have a room, dark incident light can come from either a thermal source, in this case sun was put to here, or I selected the headlight for Maróti Quattro, this is a laser light, or it comes from a laser. We do not see the source, just the radiation which comes into the dark room. Can we decide whether it will come from laser or a thermal light source? Practically we can't. Or we have to make very delicate measurements and investigations to do that. Or generally asking how to decide from inside what goes outside. This is an interesting and perhaps important question from theoretical point of view, but it doesn't have too much practical use. So if you are a physicist, a major in the audience of a physicist, you can be pretty ambiguous, so that this could be an important problem. Who cares about it? At the beginning of the summer school, maybe you do not do such kind of question, but after 2 weeks, perhaps you will get the point where you say, oh, who cares about it? But it is not so easy to put such kind of question, such kind of consequence, because to answer these questions, it can have many practical consequences. I will take a medical consequence to this principal question. For example, I selected among the many medical applications one, the healing of wound, the wound healing by light therapy or laser therapy. The essential question is, which property of the laser light is essential? This is a normal question, but it's better to say, this is why I highlighted it in red, if any. So, are there actually any properties which make the distinction between the thermal source or laser light? You can hardly answer the question. Okay, some scientists are pretty sure that I can answer it, so that it's definitely we have to illuminate by laser and not by thermal light. But according to my judgment, to use lasers, this is just a question of practical importance. So then it's easier to use lasers, easier to handle, to manipulate than light source. And this is the reason why lasers are used for such kind of medical applications and not thermal light sources. Okay, now let's turn back to the principal questions and try to answer. Beginning with the general physics of the laser operation, because the properties are determined by the generation of the light, in this case the laser light, and we will use the simplest case which can be imagined. More simple case doesn't exist. So a two-term system, we have the molecule or atoms whatever we have in the light in two states, either in ground state or in excited states. The energetic difference between the two states is h times mu. And the transition between these two states, as you surely well know, can be either induced or spontaneous processes. Absorption is always induced absorption, so excitation comes from the radiation field, so the absorption is always induced. But the emission from these states can happen in two ways, either in induced way or by spontaneous way. In an everyday life, we will mainly meet with the spontaneous form of emission, and induced form of emission is very seldom. There are different conditions which is very important in the laser operation. I will not deal with it. Tomorrow you will surely listen to this lecture from Professor Maróti, and you will get more acquainted. But what is important here is Einstein coefficients. B is a transition coefficient refers to the induced processes, and the emission versus the induced emission, Einstein coefficient, depends on the cube of the energy difference, energy gap between the current state and the excited state. This means that if the A is small, so you have selected two energetic levels which are very close to each other, so A is small, then A, this means that the spontaneous emission will be small compared to the induced emission. This means the lasing or laser transmission can be expected with higher probability. In this case, the two layers which are closer to each other. And in opposite case, if A is large, so the energy levels are pretty far separated from each other, then the probability to occur, the spontaneous emission becomes larger and larger, and the probability for lasing is smaller and smaller. The second property of the induced emission can be read here, that it will keep the direction and phase dependence. You can read the text, I will not read it. Another point which is important to discuss here, the final bits of the energy levels. Here I just showed you a single energy state, but this is overlapped by a lot of vibrational states. It's spread out. And the method of spread out, the half-width, is denoted by delta mu or delta A. This is attributed to the line broadening, is attributed to the different energy levels of the excited state. The important point in this case is the Heisenberg uncertainty principle, because the lifetime of the excited state is denoted here by delta or simply by tau, the lifetime, and the energy, this is in this case A, are commeasurable quantities in the quantum mechanics, and these are commeasurable quantities, similarly as, for example, the race coordinate and a pulse. Then they have obey the Heisenberg uncertainty principle. This means that they can be simultaneously measure the arbitrary small variation or uncertainty. This means that the product of uncertainty should be limited, and this limitation is determined by the Planck's constant. This means that the lifetime of the excited state multiplied by the energy uncertainty or energy spread out of this state is very fine and cannot be smaller than the value which is determined by the Planck's constant. This is a fundamental law which gives you the connection between the lifetime of the excited state and the line width or time width can be said in the set form of the excited state. Now, this is what we learned from this slide, and then we go back further. The diffraction limit or the there any compromise? So what is the color? The normal human eye watching, of course, so not really ask what kind of color do you see. So what kind of color is there? 600 nanometer?
Orange.
Yeah, orange, between orange and red. Yeah. Cool, good. So I told you, warned you that I provoke you. So not to fall asleep, that's important. So if you put an orange or light blue, red light, then we can focus 1.5 micrometer, or we can rapidly focus the spot size of a couple of micrometers square, which is, can you tell me an object which falls in that range, say 1, 2 micrometer? An object, please. If it's a living object, it's better. For example, bacteria, or a single cell plant cells are bigger, or algae are bigger, but you know the bacteria at that size, a couple of micrometer size. So in the best case, we can illuminate a single bacteria. So that's the spot size. And the second example considers we admire the light bulb and the laser light, and what will be the brightness on the focus of our eye. In the case of the light bulb, at a distance of 5 meters, it is calculated here around, what was it, I don't know, maybe at, I have to read it, 10 watt/meter square. But if you look at the laser light directly in, then the brightness in the retina will be much larger, say 3 times 10 to 4 watt/meter square, which is an essential difference and additional to the UV light which comes in. This high intensity can be damaging for the retina. No, this was the high energy, high brightness, etc. It now comes another property, the coherence. The coherence we will check in spatial and in temporal versions. The temporal version of the coherence is measured by the Michelson interferometer, and the spatial coherence of the light source can be measured by Young's double slit interferometer. Now let's start with the first one, the temporal coherence. What is the definition? The temporal coherence is practically the inverse, the reciprocal value of the line peak of the spectral line. So tau c equals 1/delta nu. Here you cannot see too much, but the c, the subscript c's, they're not seeing here because of the finite size of the projections. So the temporal longitudinal length of coherence can be calculated for the time of coherence. And it can be measured by a Michelson time interferometer, which is a well-known arrangement with a beam splitter with 2 mirrors. One is fixed, the other is movable. From the light source, which has a wave packet with several oscillations, will be cut into 2 parts, 2 arms, reflected from the 2 mirrors, and then again they are meeting or showing an interference pattern. If the difference in the light path is comparable to the depth of coherence, then you will see sharp fringes. In other case, it is too large, then these fringes will disappear and no interference pattern can be seen. So the interference is a good indication of the temporal coherence, and it can be measured directly with the Michelson interferometer. This is the temporal coherence. The spatial coherence is a little bit different. The spatial coherence describes how the radiation field deviates from an ideal one. Ideal can mean a plane wave or a spherical wave, because these waves has a very large spatial coherence. If there is some distortion in these ideal cases, then accordingly the spatial coherence will be less and less. More definitely to measure in the Young's double slit interferometer, which can be also calculated in a more exact way in this slide. What is it? We have 2 slits denoted by S1 and S2. We have a light source, a point light source denoted by S, which is moved from the central position a little offside to S prime state. It can be also imagined that we have a finite size of light source. We will consider some